Hey everyone, today we're here to look at questions 31 through 40 on the AP Statistics Practice Final. This is for semester A. So we're going to get right into it with question 31. Mr. Ayabi wants to know, does caffeine improve exam performance? Suppose all students in the 830 section of a course are given a treatment, which is 2 cups of coffee, and all students in the 930 section are not permitted to have any caffeine before their midterm exams. Suppose half of the 830 students are randomly allocated to the treatment group, and the other half are located to a control group, 2 cups of decaf. In addition, half of the 930 students are randomly allocated to the treatment group, and the other half are allocated to the control group. This is an example of... Well, this question reads a little bit weird to me because, we're saying the treatment is 2 cups of coffee, but then in this sentence right here, we're saying half of those 930 students are also going to be allocated to the treatment group, even though it says that in the 930 group, they're not permitted to have any caffeine before the midterm exam. So I guess that's just before the midterm exam. So what is going on here? Is this a voluntary response study? That's maybe the way we should approach this. And looking at this, they're not really volunteering to be part of the treatment group. So I think that's probably not the correct answer. How about a stratified sampling procedure? And were the students actually put into 2 distinct groups that are similar in ways relating to the response variable, and they actually are, because the 830 section are not permitted to have their treatment, and the 830 are permitted to have the treatment, and the 930 are not permitted to have any caffeine before the midterm exam. So the 830 and 930, they are different in respects to caffeine. However, I think I'm going to hold off on calling this a correct answer because even though stratified sampling was used, this isn't really just a sample. We're actually giving them a treatment, so I'm not sure about that. Match pair design, well, we're not really matching any people together. Maybe we're matching the entire section, not 930, with the entire section at 830, but match pair is about matching individuals, not about matching an entire group. So that doesn't sound like the correct answer. Completely randomized design, well, in a completely randomized design, we wouldn't make any distinction between the 830 and the 930 group. It wouldn't matter. So this is definitely not a completely randomized design. So we're down to a stratified sampling procedure and a randomized block design. And the reason why we're going to pick a randomized block design over the stratified random sampling procedure is because we're not sampling. We're actually doing an entire experiment here. So that sounds like the better response of the two. So a little bit confusing. The one thing I will say about this is this doesn't sound like a pretty clear experiment, not a very clean design. But that doesn't mean it's not a randomized block design. So let's move on to number 32 here. Just a reminder that no one is saying that it's a good experimental design. It just is an experimental design. So 32 says the owner of a chain of supermarkets notices that there is positive correlation between the sale of root beer and the sale of ice cream over the past year. During seasons where the sale of root beer was above average, the sale of ice cream tended to be average. And likewise, during seasons where the sale of root beer were below average, the sale of ice cream tended to be above average. So which of the following would be valid conclusions? So this is one of those favorite sayings that they have over in AP Stats. There is a correlation. It's a negative correlation here between sales of root beer and sales of ice cream. But that doesn't mean that there is a cause and effect relationship. So as we go through this first one, sales records must be an error. There should be no association. Well, association Well, there might be association between the two. There's no reason for there not to be, an association between the two. Letter B, evidently, a significant portion of customers at these supermarkets drinking root beer causes a desire for ice cream. No, that's not actually true. This is the word cause here is the problem. Nothing is causing, ice cream or is not causing root beer. Root beer is not causing higher consumption. And I think earlier I kind of misspoke. Hopefully you caught that. I did say it was a negative correlation, and apparently it's a positive correlation, because when root beer is above average, ice cream is also above average. So they are both going up together. If one goes up, one variable goes up, the other variable also will go up, will also increase. So that takes care of letter B. It's not a cause, and maybe I should really highlight the fact that we're saying cause here. That's not what's happening. Letter C, a scatter plot of monthly ice cream sales versus monthly root beers sales would show a straight line pattern. Sorry, a straight line describes the pattern in the plot, but it would have to be a horizontal line. So the horizontal line here, there's a few things that are wrong here. Firstly, the horizontal line, if the pattern is a horizontal line, that means there's no association between the two. We'll get more into that in the next semester. But there's no reason why it has to be a straight line that describes a pattern. There's nothing in here that says it would be a straight line. That is the best regression between these two. So I think that's wrong for a few reasons. So letter D, this says that it's likely that the sales of both root beer and ice cream are confounded by another variable, such as seasonal variation in temperature. So when you approach it this way, we're saying that if the temperature, let's say, for example, gets warmer, what happens to root beer sales? Well, they're probably going to increase. And also, if the temperature gets warmer, the sales of ice cream are always going to increase as well. So really what's happening is that root beer sales and ice cream sales are both responding to the seasonal variation in temperature. They're not responding to each other. They're both response variables of the same explanatory variable, which is the temperature. And then this is a negative association. That's actually the opposite of what we're seeing. We're seeing a positive association between the two. So that makes this one incorrect. So here the correct answer for 32 is D. 33. This one reads really nicely if you're studying your probability. When two coins are tossed, the probability of getting two heads is 0.25. That means that, two heads, the probability is 0.25. Let's remember that's a long-term description, not a short-term description. So for letter A, of every 100 tosses, exactly 25 will have two heads. Well, the exactly part is a part that is going to make this wrong. So this is not exactly going to be 25. Okay, the odds against the heads are 4-1, and it's actually 3-1. 75% to 25% is 3-1. So this 4-1 business here, that's not correct. It's actually 3-1. Okay, so letter C, in the long run, the average number of heads when two coins is tossed is 25. So this says long run, and I love that because that's exactly what we're talking about here, the long run. This also says average number. It doesn't give you the exact number. It says the average number. So that's pretty good. I'm going to leave that in there for now. We'll take a look at letter D, and in the long run, again with the long run, two heads will occur on 25% of all tosses. Okay, so this here makes this sound like, it's 25% is going to happen no matter what. And that's not the case. And lastly, if you get 2 heads on each of the first 5 tosses, you're unlikely to get heads on the 4th one. That's not correct. You're just as likely to get heads on the 4th trial as you are on the first 2 trials. They like to say that the coin has no memory. So it doesn't matter what happened before. The probabilities are always going to be the same with individual tosses. That likelihood of getting a head on that 4th time, that's still going to be 0.5 actually. So this is correct here. We're going to go with that one. Letter C. And I'm looking through this, and I'm going to have to eat my words here. The average number of heads right here, that makes this one kind of suspect. Because it's actually the proportion of heads is 0.025, not the number of heads. So actually C is wrong too. So I'm going to take a look at these again. Let's have another fresh look at letter D. That's the only one that seemed likely to be a correct answer. In the long run, 2 heads will occur on 25% of all tosses of 2 coins. Well, that's certainly not my favorite because it does make it seem like 25% will happen always. But I suppose since we're looking at a long run probability, as long as we get a long enough long run, it will be 25%. And that would be in the really, really, really long run here. So I guess the letter D would be a better answer than letter C, especially when you see the average number of heads is 0.25, and it should be the average proportion of heads. So that one got me. That's great. Good to know. Number 34 here. We've got a 10-sided die that has the digits from 0 to 9 on each of its faces. Unless you're playing Dungeons and Dragons or something like that, you've probably never seen a 10-sided die. That's okay. That doesn't mean they don't exist. Which of the following best describes what it means to say that the probability of rolling a 3 is 0.1? So again, this is going to be something that happens in a long run. So probability is always a long run thing, a long-term proportion. So let's take a look at letter A. If you roll the die thousands of times, yes, that's a long run, the proportion of times that you will roll a 3 will be close to 0.1. I like this one a lot because it does give me a long-term proportion, and it does say close to 0.1, not exactly 0.1. So number 34A sounds really good. Let's count out the rest of these just to make sure. I don't want to make another mistake like we did on 33. So if you roll the die 10 times, one of those 3 rolls will be a 3. And that one just seems too much like it's deterministic. Like there has to be a 3 in those 10 times. Same thing with letter C. If we roll the dice 10,000 times, 1,000 of the rolls will be 3s. And that seems like it's saying for sure, without a doubt, 1,000 of the rolls would get a 3. So if we roll the die 9,999 times, and only 9,999 have been, only 999 of them have been 3s. That means that last one is guaranteed to be a 3 because we got to get to 1,000. And that's not the way that probability works. So that's not going to be correct in my book. Letter D says it would be impossible to roll the die 100 times and not get any 3s. Impossible? Well, not impossible. Improbable, yes, but not impossible. So I would say that this is probably not correct. And then if the first 2 rolls are 3s, the probability of getting a 3 on the next roll is slightly less than 0.1, and that drives me crazy. That's not true. The probability on every roll is 0.1. So yeah, it seems as though letter A is the correct answer. And we'll highlight this. There we go. And that moves us to number 35. Mr. Hanks has placed a large number of plastic discs in a hat and invited you to select one at random. She informs you that they have numbers on them, and one of the following is a probability model for the number of discs you have chosen. So which one is a correct probability model? Okay, so for this one, let's remember the probability models, how they work. So in a probability model, every probability needs to be between 0 and 1. They can be 0 and they can be 1, but they have to be in this set of numbers. And finally, if we add all the probabilities together, they should add to 1. So for letter A, when we see the number on the discs, and we have 1/4, 1/4, 1/4, 1/4, 1/4, this is bad because all those probabilities add to 1.25. That's what's wrong with letter A. Letter B, all of these probabilities, oh, look at these probabilities, 1, 2, 3, 4, and 5. Those are not between 0 and 1. So I'm not a fan of that one. Let's look at letter C. 0.1, 0.2, 0, 0.3, and 0.4. And if I'm looking at these, all of these probabilities, they do add up to 1, I believe. Yeah, they add up to 1. All the outcomes look fine. So yeah, this one looks pretty okay to me. Let's check letter D. We've got 0.1 plus 0.11 plus 0.25 plus 0.05 plus 0.26. Yeah, well, these probabilities, well, they only add up to 0.77. So this one is also incorrect. And letter D, not only do we have a -1 right here for 3, we also have, probability of 1 plus 1. Well, both those probabilities can't be equal to 1. So this is also not a correct answer. So you can see by process of elimination here, letter C's got to be our correct answer for question 35. So let's highlight this one. And there we have it. Number 36. In a certain town, what do we have? 60% of the households have fiber optic internet access, 30% have at least one high-definition television, and 20% have both. So what percentage of households have neither fiber optic nor high-definition television? So for this one, this sounds like we need to make a chart. So if I take a look at the chart, we've got fiber optic and no fiber optic, which would be fiber optic complement. We have HDTV and HDTV complement. We have in the bottom right our totals adding up to 100% or just a 1. 60% of the total town has fiber optic, so that'll get us 60% in the fiber optic. Ooh, we're in the wrong place, sorry. And that would mean 40% do not have fiber optic. Next, we see that, what percentage here? 30% have at least one high-definition TV. So for high-definition television, this is going to be 30% right here, which means 70% do not have high-definition television. And if you're watching this in the far future, you should know that there was a time when not every household had high-definition TV. Some households had high definition, some households did not. But here is the part statistically where things really matter. 20% have both. So it's fiber optic and high definition television. When you see that both category, we're talking about here in this inner box. So 20% have both fiber optic and high definition television. That's 20% of the entire population. So if 20% have high definition and fiber optic, right here, that means 10% have high definition and no fiber optic. So this line right here has to be 20% plus 10% has to total up to 30%. Okay. Looking at the fiber optic column, we've got 20% have fiber optic and HDTV. That means 40% have to have fiber optic and no HDTV because the fiber optic column has to add up to 0.60. And now that I have those three filled in over here, this should make sense for the, let's do it for the high definition television. 40% who have fiber optic and high definition television plus this number that has no fiber definition and no fiber optic, those two need to add up to 70%. So the missing number here has got to be 30%. And you'll know you did it right because this column also makes sense. 10% plus 30% is equal to 40%. So now the question is, what percentage of households have neither? Neither would be fiber optic and no fiber optic, no HDTV. That is 30%. So our 30% is our correct answer. Okay. The following information is meant for questions 37 and 38. You've got a group of 25 pickup truck owners who were asked what brand of truck they owned and whether it had four-wheel drive. Here is the results in this two-way table. And you're going to randomly select one truck driver. So what is the probability that he owns a Dodge or has four-wheel drive? Okay, we can go with our formula here. This probability of Dodge or four-wheel drive, that's the probability of a Dodge plus the probability of a four-wheel drive minus the probability of a Dodge and a four-wheel drive. So let's get those numbers. The probability that they have a Dodge would be 30 out of 125. Now the probability that a randomly selected person has four-wheel drive is 80 out of 125. Minus the probability that a randomly selected person is Dodge and four-wheel drive, or a four-wheel drive equipped Dodge. That is 20 out of 125. We add that all together. We get 0.9, which is, sorry, that was embarrassing. We get 90 out of 125. So our correct answer is letter D, 90 out of 125. Let's take a look at 38. You randomly select one truck driver, and which of the following is true about the events? Owner has a Chevy and owner's truck is four-wheel drive. So the first thing I'm going to check is, are they mutually exclusive? Well, let's see. Probability of Chevy and four-wheel drive is equal to 32 out of 125. That's 32 out of 125. And that's not equal to 0. Mutually exclusive means this AND probability is equal to 0. And since we're not equal to 0, this is not mutually exclusive. So any of these answer choices that says these two events are mutually exclusive, it's got to be wrong. So looking at the two answer choices that are left, which is not mutually exclusive and not independent, that means we have to check if they're independent. So let's get the independent probability. Two events are independent if the probability of A is equal to the probability of A given B, and that's equal to the probability of A given B complement. In terms of Chevy and four-wheel drive, we have to check the probability of Chevy given four-wheel drive, and probability of Chevy given the complement of four-wheel drive. So coming up to my chart, the probability of a Chevy is 50 out of 125. The probability of Chevy, given that the car is a four-wheel drive, is 32 out of 80. And then the probability of a Chevy, given that it's not a four-wheel drive vehicle, is 18 out of 45. So if we come back down and put those probabilities in here, these are all 40% probabilities. So that means that they are independent. So if we know someone has a four-wheel drive vehicle, then it doesn't change the probability that we have a Chevy. So these are not independent, or rather this one says they are not independent, so answer choice D is incorrect. Therefore, letter choice C has got to be correct. Now, this was probably the hardest one we've had all day long, or at least for this video. You got to know the definitions here of mutually exclusive and independent, and you have to be able to show that they are independent. So that brings us to question 39. Got a couple more here to go. In a particular game, a fair die is tossed. If the number of spots showing is either 4 or 5, you score 1 point. If the number of spots showing is 6, you score 4 points. And if the number of spots showing is a 1, 2, or a 3, you score 0 points. And you're going to play the game twice. What is the probability that you score 4 both times? So the first thing to notice is because the die has no memory, the games are independent because the outcome of game 1 is not going to affect the outcome of game 2. So this means that the probability that game 1 is equal to 4 and game 2 is equal to 4 is going to be the probability that game 1 equals 4 multiplied by the probability that game 2 is equal to a 4. So what's the probability that you get a 4 in game 1? Well, you get 4 points if the number of spots showing is a 6. So that means the probability of getting 4 points on the first game is 1 out of 6. Because there's only one way to get 6 spots showing out of the 6 outcomes. And we're going to multiply this by the probability of getting 4 points on game 2. And you get 4 points on game 2 if the number of spots showing is a 6. And that probability is 1 out of 6. So that, when we multiply that together, we get 1 out of 36. So the correct answer here for 39 is letter A. Which brings us to question 40, the last one we're going to do in this video. A randomly chosen subject arrives for a study of exercise and fitness and begins walking on a treadmill at a brisk pace. Okay, so which random variable of these is discrete? So the discrete means that some outcomes in a range are possible and other outcomes are not possible. The classic one here would be the set of integers. Those are discrete. So let's see, the maximum heart rate in beats per minute. Okay, that sounds pretty good. Some are possible, some are not possible. You definitely can't get beats per minute like, I don't know, 32.2. That seems weird. The next one here is going to be VO2, which is the maximum volume of oxygen consumed in number of minutes during exercise, which is generally a number between 2.5 liters and 6 liters. Now for letter B, I mean, there's no end to this. Like you could say 2.7 liters or 2.71 liters or 2.711 liters or 2.7111 liters. There is not a set number of outcomes here. Any outcome that is between 2.5 and 6 is okay. So this one I think is wrong. Walking speed in miles per hour. Now, in miles per hour, we could definitely, just like VO2, we could say like 3 miles an hour, or 3.5 miles an hour, or 3.55, 3.555. All of these are definitely possible. So that one doesn't seem like it's going to be a discrete number. Next one, the amount of time in minutes a subject walks on a treadmill before his or her heart rate reaches 120 beats per minute. Well, over here, you could have 1.2 minutes, 1.22 minutes, 1.222 minutes. That doesn't sound all that great. And then the last one here is the time between subject's heartbeats after 10 minutes of walking. And you can definitely dice up a second as much as you want. Milliseconds are definitely a thing that exists. So that time is not going to be great. The only thing that makes me worried about letter A is the maximum heart rate in beats per minute. What's wrong with a heart rate of 22.9 beats per minute, other than that's really low? No, I don't think you could do that, because we're not talking about an average heart rate. We're talking about how many times the heart beat in a minute. So here, this one would probably be our correct answer, and a quick check. Yeah, this looks to be correct. So that is our video for today. Questions 31 through 40. This was a long video, but this is the probability part, which most people are well, these tend to be the hardest questions around. So that's going to be it for us this time. See you next time for more review on AP Stats.